Hello students, in the last session we completed the concept of spring and we did see the understanding behind the power, okay? So that logic which we need to know. And then we saw the first part of the collision, okay? So that was like completely inelastic collision, which was, so those were the stuff that were dealt in the last classes, okay? So in this session we will do the elastic collision, which means the third type of collision, right? Okay, so that will be dealt. All those derivation part will also be done in this class. Finally we will see one small topic which is called as coefficient of restitution. That too will be done. And then we have like trigonometric relations which needs to be memorized, okay? So you have around like 5 trigonometric relations that you need to memorize, because while doing the sums that will be handy, okay? Certain conversions need to be memorized. So you have like 5 trigonometric relations. I'll tell you what are all those 5 trigonometric relations that you actually need to memorize, okay? Got it, right? So we wouldn't see the proof for those trigonometric relations, because those proof will be dealt in your math classes, and then if you just Google it, you will be able to get those proof, okay? So proof is not needed, but those 5 relations has to be memorized, okay? So these are all the things that we will see in this class, okay? Fine, so let's see the first topic, which is like elastic collision, okay? So I have already told you what is meant by elastic collision, right? So when two objects is going to collide each other, there will obviously be the deformation because of the force impact, right? So when you have that deformation, so when the deformation is stored, isn't regained, then in that situation it's called as completely inelastic collision, which means the deformation will be there as such, and then both will start moving at certain constant velocity. So that is called as completely inelastic collision. In the case of elastic collision, what happens is, so both those masses is going to strike on each other, and then it will bounce back, and then it will regain its original shape. Again, the energy wouldn't be lost. It will just move with the same amount of energy, okay? So uh, the energy split will be equal, okay? So before the collision, two masses would have certain velocity, and then there will be certain kinetic energy, and after collision those two kinetic energy might have split in some fashion, but the thing is, summation of kinetic energy initially will be equal to that of the summation of the kinetic energy after collision, okay? So those two things will be balanced and matched. So that kind of condition is called as elastic collision, okay? Which means all those deformation will again bounce back and regain its original shape, and then it will have the same amount of velocity, right? It will have the same amount of kinetic energy into it, okay? So if that was the case, there isn't any other loss to the surrounding in other form of energy. If that was the case, then obviously that is called as elastic collision, okay? So we might know that always energy is going to be conserved. In the situation, energy will be conserved, which means those energy wouldn't be used even for the breaking of molecules and things of that sort, okay? So that's the condition over here, right? So you should have that understanding. Fine, so we'll see the elastic collision, okay? So elastic collision, let us take those two different scenarios. So the first case is like before collision, and the second situation is like the after collision, okay? So before the collision, what would have happened is, okay, again, even in this situation, I'll just take it in this fashion. So second mass is going to have the velocity is going to be at rest. Therefore, the velocity of the second mass will be like 0. Okay, so u2 will be equal to 0. So the velocity of the second mass is 0. That is fixed. So obviously, this first mass has to move towards the second mass so that the collision is going to happen, right? So here, in this case, the first mass is going to move towards the second mass with certain velocity. That's going to be e1. Okay, so this is going to move towards the second mass, and those two stuff are going to collide with each other, right? So after the collision, obviously here these two will gain some different masses based on the force impact and all those stuff, and then the energy would have split between these two masses, and those two masses will travel with certain velocity, right? But in this case, it will regain its original form. These two objects will regain its original form, and there wouldn't be any other loss to the surrounding, okay? If that was the case, then what will be the velocity of these two masses? That's what we are supposed to find over here. So we'll do some derivation, and then we'll end up getting those answers, okay? So here, for the simplistic situation, let us take it this way. The velocity of the first mass, final velocity of the first mass will be like v1 towards the plus x direction, and the final mass velocity of the second mass will be the v2, okay? Let us take, I have taken it in this fashion such that these two are in the positive direction itself, which means if it could be, it is possible that one of the velocity might have been in the opposite direction. That stuff is possible, but I'm just going to simplify the situation where in the case these two masses are going to be in the positive direction. Okay, fine. So if it was in the other way around while doing the sum, you'll end up getting the negative sign. That's it, right? So this is the simplistic situation that I've told you. Initially, one was at rest, the other one was moving. Okay, after the collision, both were moving in certain direction, but the point is both were having the velocity and the energy got split between those two masses in the form of kinetic. Okay, so you should be clear with this understanding. Then let us do those two conservation. One will be like the momentum conservation as usual, and the next one will be the energy conservation. Okay, kinetic energy conservation, right? So let me do the solving. So in the case of the first one, the initial momentum will be equal to m1 u1, right? The second mass isn't going to have any momentum because its velocity is 0 with respect to the first mass. Okay, which will be equal to the final momentum, that will be equal to m1 v1 plus m2 v2. Okay, so this should be clear. Then let us do the kinetic energy conservation. Okay, so with the case of kinetic energy conservation, initial kinetic energy will be equal to the final kinetic energy, right? So Ki should be equal to the Kf, final kinetic energy. Let us do it straight away. So we'll have half, okay, m1 u1 square. So obviously we will not have m2 half m2 u2 square because that's going to be 0, which will be equal to half m1 v1 square plus half m2 v2 square. Okay, got it. Now let us do the cancelling stuff for the half. So these half will get cancelled out, and then we'll just be left with this part, right? m1 u1 square, m1 v1 square, and then you will have like m2 v2 square. So that's the only part that will be left. So let me replace this m2 v2. Okay, so I'll do certain replacement to get the v2. Okay, in a favorable fashion. Fine. So here you have got like m2 v2 over here, right? So even if you have got other terms also. So but in this situation, I'll just do the solving according such that I'm going to get the v2, velocity of the second mass, with respect to the u1 and then the v1. Okay, got it. So what I'm going to do here is I'm just going to replace this. I'll have to get this v2, right? So instead of this entire term, I'm just going to replace it such that m2 v2 will be equal to m1 u1 minus m1 v1, right? If I'm just going to replace that one, then I'll just be left with this entire term here instead of m2 v2 and then one more v2 into it, right? So that's how I'm going to do the solving over here, right? Okay, the understanding should be clear. Okay, let me do the rearrangement thing over here. So I'm just going to replace this m2 v2 over here. Fine. So if I do the solving, you'll have m1 u1 square, which will be equal to m1 v1 square, right? So that term will be the same thing, plus you will have m1 u1 m1 u1, okay, minus m1 v1, and then you will have the v2. Okay, so this will be this will be the term that will be left. Okay, right? So next step, what I'm going to do is I'm just going to cancel out all those m1 in it, right? Because that term keeps on repeating. Fine, so that will obviously cancel out. So you'll have like m1 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 m1, all those terms will get cancelled out, right? Now let us do like little bit rearrangement. You'll end up getting the answer. Okay, so if I do the first rearrangement, which will be like u1 square minus v1 square, which will be equal to v2, okay, u1 minus v1. Fine. So obviously this thing is something that seems to get cancelled out, right? So you have got like a square minus b square, and then you have got like a minus b. What is the formula for a square minus b square? That will be equal to a plus b into a minus b, right? So that's the relation that I'm going to substitute it over here. So if I do substitute that one over here, you will have like u1 minus v1, and then you will have u1 plus v1, which will be equal to v2 u1 minus v1, right? Let me cancel out those two stuff. So these two stuff will get cancelled out, and I'm just done with the solving part. So the final velocity of the second mass v2 will be equal to the initial velocity of the first mass u1 plus the final velocity of the first mass. Okay, so this is direction sensitive, which means I'll have to be careful with the signs that I'm going to plug in over here, right? If the velocity of the first mass is going to be in the negative direction, then I'll have to plug it in properly. So the v1 has to be like negative, that value which I need to put it over here, right? This one should be clear. Now I have got the V2, which means the final velocity of the second mass. Right, next, just I'm ready to substitute the same thing into this first equation that I've got over here with respect to the momentum conservation. Okay, so m1 u1 is equal to m1 v1 plus m2 v2. Right, next what I'm going to do is I'm just going to get the relation for the u1. Next I'm going to get the relation for the v1 and v2 in terms of u1. Okay, so to get that stuff, I'll just substitute v2, the same relation. Okay, so v2, which is going to be equal to u1 plus v1 in the momentum conservation stuff. Okay, so here I'll have to plug it for this v2. Okay, if I'm just going to do it, I'll have like m1 u1, which will be equal to m1 v1 plus m2 v2. Instead of this v2, I'll have to substitute u1 plus v1. Right, so that's the change that I need to make over there. So you'll have m1 u1, which is equal to m1 v1 plus m2, and then you will be left with u1 plus v1. Okay, next let me do the inner multiplication. If I do the inner multiplication, you'll have m2 u1 plus m2 v1. Okay, so here obviously what I need to get is m2 v1, right? m2 v1. To get the v1, I'll have to rearrange this equation, right? I'll rearrange it in this fashion. Okay, such that you are going to have m1 u1 and then m2 u1 on the one side. So you will have m1 u1 minus m2 u1, right? Okay, so we will have m1 u1 minus m2 u1. So that will be something like this: m1 minus m2 and then the u1, right? I have just factored out u1 straight away. So you'll have like m1 u1 minus m2 u1. So that thing is done. Next you have got m1 v1 plus m2 v1, right? So here if I just factor out v1, you'll have m1 plus m2 and then v1. Okay, so the next step will be m1 plus m2 and then you will have like v1. Right, now I'm just done with this part. So v1 will be equal to m1 minus m2. Okay, that will be in the numerator. Then you will have like m1 plus m2, that will be in the denominator, and then multiplied by u1. So that will give you the necessary v1 which is needed over here. Fine, so next let me do the same kind of substitution over here to get the v2. Okay, so if I need to get the v2, I'll just use this equation itself. Okay, so instead of v1, let me do the rearrangement. Okay, so here I've got this equation which is like v2 equals u1 plus v1, right? I have substituted v2 first in this term, so v2 was equal to u1 plus v1. Next what I'm going to do is I'm just going to rearrange the v1. Okay, if that was the case, v1 will be equal to v2 minus u1, right? v1 will be equal to v2 minus u1. So that's how I need to do the rearrangement. So here you will have v1 which will be equal to v2 minus u1. Got it? This part should be clear. So instead of v1, I'll just plug in v2 minus u1. So v2 minus u1 will be equal to m1 minus m2, that term. So this stuff, that's going to repeat it as such. Now I'll have to get the v2, right? So v2 will be equal to, just do the rearrangement thing, you'll get the answer, right? So v2 will be equal to this entire term plus u1. So let me factor out the u1 and do the cross multiplying stuff, you'll get the answer. Okay, so here you will have something like this. So if I just factor out u1, you will have 1 plus m1 minus m2 divided by m1 plus m2. Okay, that will be inside the bracket, and then you'll have u1 because I've factored it out, right? So if I do the cross multiplication, you'll have m1 plus m2 and then plus m1 minus m2. So m2, those two stuff will get cancelled out. Then you'll just be left with 2m1, okay, in the numerator. So the final answer will be simple straight away. That will be equal to 2m1 divided by m1 plus m2, and then it will get multiplied by u1, right? So that will be the final velocity of the second mass, which is like v2. Fine, so 2m1 divided by m1 plus m2 u1, that will give you the velocity v2, right? So these formulas, it is better that you memorize it. Okay, so if you just know the one formula which is like v2 is equal to u1 plus v1, final velocity of the second mass will be equal to the initial velocity of the first mass and the final velocity of the first mass. one and only if you know that equation, then this one should also be memorized, okay? Because or else you'll have to do those steps to get to the final answer, fine. So V1 will be equal to, in the numerator, those two stuff will get subtracted. In the denominator, it will get added times the U1, okay? So if you just know those two equations, just plug in this V2, you'll end up getting this third equation, okay? It is better that you memorize these three equations, because in the while doing the sums, it is, if you just know it by heart, you'll be able to get the answer straight away, right? That you need not spend time in deriving all those stuff, right? So V1 was equal to U2 plus U1. I mean, V2 was equal to U1 plus V1. That has to be memorized. From that, if I just substitute it into this second equation, I'll end up getting the third equation, right? So these are some things that you need to know. Finally, let us see some special cases, okay? So the special case over here is, let us consider it this way. The initial mass, I mean the mass M1 and the mass M2 are just the same mass, okay? So both those stuff are going to be same for the case 1, which means M1 is equal to M and then M2 is also M. In the situation, it is like a perfectly elastic relation and both the masses has the same mass, okay? M1 is equal to M and then M2 is also equal to M. So that's the condition when both are equal and same. Let us plug in M into those two above equation and let us find out, okay? For the V1 and then the V1 and then the V2, okay? For V1, it will be like M1 minus M2, right? So M1 minus M2, these two masses are same, therefore this term will be 0, therefore this entire term is going to be 0, right? Then in this situation, V1 is going to be 0. The velocity, final velocity of the first mass is going to be 0, okay? Now I'll have to get the final velocity of the second mass. So to get the final velocity of the second mass, obviously all the m are same, therefore you are going to have like 2m in the numerator. Same way, m plus m will give you the 2m in the denominator. These two stuff will get cancelled out, therefore v2 will be equal to u1. So v2 will be equal to u1 in this situation. So in this special case, what has actually happened is velocity got interchanged, okay? So the velocity gets interchanged in this case, right? So this thing has to be clear. So here, so the situation is such that when two masses are same and then the second mass is at rest, okay? If that was the case, when the first mass is going to travel with certain velocity and when it hits the second mass, okay, this is like perfectly elastic collision. If that was the case, then the first mass which hits the second mass will come to rest. In turn, the second mass will gain the exact kinetic energy and then it will start traveling with that particular kinetic energy, okay, with that same velocity. So here, even in this situation, the energy wasn't destroyed, it was conserved, okay? So whatever the kinetic energy that the first mass possesses has been transferred to the second mass after the collision. So this is how this case is going to be, right? Fine. So now let's see the second case, which is the case 2. Got it? So in the case of case 2, I'm just going to compare it such a way that the first mass is very less when compared to the second mass, okay? So in this case, I'm just going to consider the mass 1 to be a ball, okay? So the mass 1 over here is actually a ball which has a smaller mass, fine, and the mass 2 is like very huge when compared to this first mass, such that when I throw this first mass against the second mass, it's not going to cause any impact to the second mass, right? If that was the case, then m2 has to be huge. Let's take it in this fashion. It is going to hit a wall, okay? So that wall is actually that wall is actually built on the earth, right? Therefore it is as if like this particular wall is going to hit the earth, right? So the mass of the earth is extremely huge, or mass of that wall is extremely huge, it's not going to move, fine. So if that was the case, then what will happen to the case of the first ball? Obviously we know by intuition, with whatever velocity it hits, it's going to get bounced back, right? So that's what should happen over here. It should have the same kinetic energy, but it should get reversed, fine. So let us verify, does it work out in the situation or not with respect to the equation that we have generated, fine. So in this first mass is going to be ball. The second mass is so huge when compared to the first mass, so let us consider it to be a wall that is built on the earth surface, okay? So wall on the earth. So that will be the second greater mass that I'm going to choose, as if the second mass is so huge whose mass is equal to that of the mass of the earth. That's the situation that I've considered it over here, right? That idea should be clear. Let us find what's the velocity of the first mass with respect to the equation that I've generated over there. Okay, so M2 is much greater when compared to M1. Okay, so if that's going to be the case, M1 is very negligible, right? It's like subtracting. I'm just going to give you some arbitrary condition over here. It's like subtracting like 1 minus 1 million, something of that sort. You will still have the negative 1 million over here, right? So in the denominator, you're just going to add it, right? 1 plus 1 million will still give you 1 million, will still give you 10 lakh kg, right? So if that's going to be the case, then obviously in this situation, in the numerator, just the sign got flipped. M1 minus M2 will give you the negative sign over here. In the denominator, you have the same term, okay? So there is something of negligible decrease in the numerator and negligible increase in the, negligible decrease in the numerator and negligible increase in the denominator. That's how it's going to be, as if such that these two magnitudes are same. Therefore, numerator and denominator will get cancelled out because same mass. Okay, there is like negligible changes in the numerator and denominator, which need not be considered. Therefore, only thing that's going to happen over here is just the sign change is going to happen over here, right? Therefore, you will have like negative u1 in the case of the velocity of the first mass, right? So this got bounced back with the same velocity in the opposite direction. So that's pretty obvious. So here in this situation, that's going to be like minus u1. Then obviously v2 has to be 0, right? So let's verify that one also. So here you have got like 2m1. So you have got a negligible mass, so 2 times the negligible mass, and in the denominator you have got such a huge quantity. Okay, so 1 divided by 1 million, right? What is like 1 divided by 1 million? That's like a 0.000. It's like a very tiny parameter, right? So obviously the u1 has to reach the 0, which means this term, this the velocity that got gained by the bigger mass is going to be negligibly small. Therefore that term is going to be 0, right? So obviously over here velocity v2 is 0. Okay, so the velocity v2 over here is 0, right? So you should be clear with this notion idea that I've told you, right? Therefore, v1 was equal to negative u1, where in the case of v2 it was equal to 0. So it is pretty obvious when you're going to throw a ball against a wall, it's not going to cause any impact to the earth, right? Only thing is, if energy has to be conserved and the same way it hasn't released to the surrounding, then in that situation it will end up gaining all those energy back, and then it will regain its original shape, and then it will bounce back. It will bounce back to me with the same velocity or the same kinetic energy with which I have thrown it. Okay, so that's the idea that you need to know with respect to the elastic relation. So you should be clear with those three derivations that I've made over here. You should know the final result also. What is the v1, what is the v1 and what's the v2, and then same way you should know this relation v2, which is equal to u1 plus v1. Okay, so all these three formulas has to be memorized. Same way those special cases, it is good to know those special cases, what's going to happen if such and such condition was given to you, right? Okay, right, you shouldn't have any doubt on this part. It should be clear. So now collision part is done. So only part that is left over here is some basic understanding behind the coefficient of restitution, which we will see in the next page. Okay, the next concept that we are going to see over here is actually the coefficient of restitution. Fine. So this concept is based on the relative velocity, right? So if you have a clear cut understanding of relative velocity, then obviously this will be easy. Fine. So it's just the one step that we are going to see over here. So here you have got like the first condition, which is before the collision, and that next condition is going to be like the after collision. So, okay, so let me put it in this fashion. So you are having like two masses, m1 and m2, right? Both are moving towards each other with certain velocity. So when you are going to look from the outside of these two systems, if that was the case, then it seems to be that these two masses are moving towards each other with certain velocity, right? So let us put the velocity to be like u1 and u2. So we are going to look at this mass from another inertial frame of reference, which means some frame where I'm static. Okay, so that's going to be the case. If that was the case, these two masses are going to travel towards each other with the velocity of u1. For the mass m1 it's going to be u1, and for the mass m2 that's going to be like u2. So that's how it is going to be, right? So these two stuff are going to collide with each other. Got it? Then what will happen after the collision? Obviously, for someone who is looking from the outside frame of reference, these two masses will get separated and then it will travel with some velocity, right? So it could be like elastic, inelastic, whatever case it is. So whatever condition it could be, if it was like completely inelastic condition, these two things will get joined together and it will travel at constant velocity, right? In the situation, It could be elastic or it could be inelastic, that doesn't matter, right? So we are going to get a factor from it which is called as coefficient of restitution based on the collision that's going to happen. Got it? So here after the collision, the mass m1 will have a velocity that will be equal to v1. Okay, same way the mass m2 will have a velocity that will be equal to v2. Fine. So this should be clear. What I'm going to consider over here is the relative velocity before collision and the relative velocity after collision for someone who is standing inside the mass m1. So that's how the condition I'll have to consider, right? For someone who is standing inside the mass m1, he sees such that this m2 mass is moving towards him. If he consider himself to be at rest, that's the relative velocity concept, right? We have learned and discussed that one clearly in the chapter of motion in a plane, right? You should be clear with that concept. The relative velocity comes into picture when you're just going to consider one person at rest, then what will be the velocity for the second person. Okay, so that's how we'll have to consider it. That is meant by relative, right? So same way I'm just going to consider this logic. So here I'm just going to consider the first one to be at rest, and then first mass to be at rest for someone who is standing inside, and then when he looks at the second mass, what will happen to the second mass? It seems to be traveling with extra speed in the situation, right? So this e1 will also get added. That's how I'll do the relative velocity, right? So when I'm about to find the relative velocity, that will be like u2 minus u1. So that will give me the relative velocity for for a person who is standing inside the mass m1, right? So if I just going to consider this one to be at rest, then the relative velocity will be like u2 minus u1, obviously, right? So here in this case, u2 is going to be in negative direction, some velocity minus u2, and this one is going to be positive, therefore minus u1. Obviously the velocity will get added, right? So that will be the relative velocity before collision. Fine. So the formula that I'm going to find it over here is actually relative speed of separation. First I'll consider the separation, then I'll consider the approach. Okay, so the formula that we will get is actually something like this: relative velocity or speed, whatever it is, just the same notion, right? So here I'm just going to consider just the one axis where it is going to collide, right? So if that was the case, relative speed will just work out properly, right? So relative speed of first one is like the separation, therefore you'll have relative speed of separation, okay, divided by relative speed of approach. Okay, right? This is what you need to know. So what will be the relative speed of separation? So relative speed of separation is after collision, right? So after collision, I'll have to get the relative speed, which means I'll have to put one guy to rest, and then I'll have to find the relative speed, right? So if I have to get it in such fashion, then what will I do? I'll just subtract the final v2 minus v1. So in that situation, I'll get the relative velocity with respect to the first mass, right? So if I have to get the relative velocity, what will I do? If I have to get the relative velocity of the second mass, velocity of the second mass with respect to the first mass will be equal to velocity of the second mass minus the velocity of the first mass, right? So that will, if this should be the case, how I generally consider, right? So the same logic, I'm just going to plug it over here. So it's going to be like v2 minus v1, that will be in the numerator. Okay, so relative velocity of the separation will be like v2 minus v1, that will be in the numerator. So you will have v2. Okay, so let me take the blue color. So you will have v2 minus v1, okay, and then in the denominator you will have the relative speed of approach. Okay, so the relative speed of approach will be u2 minus u1, right? So in the denominator you will have like u2 minus u1. So this formula should be clear. So you will have like only one problem into it. So in the final case, if I just find out the relative velocity of separation, which will be, okay, let us consider this situation to be like elastic collision. Okay, so if I consider this one to be like elastic collision, obviously I know the energy has to be conserved. The first guy is standing inside this mass m1, same way this guy is also standing inside the mass m1. So obviously he is considering this mass to be at rest, which means this condition, entire condition, has to be elastic. Okay, so whatever the velocity split, it could be for someone who is looking at this mass from the outside, it doesn't matter. For someone who is standing inside, after the collision also the energy has to be conserved. Same way before the collision also energy has to be conserved, which means this mass should have the same kinetic energy into it. Initially it could be in this fashion, it is moving towards the plus minus x. Finally it could move towards the plus x direction. Only thing that has happened over here for the elastic collision will be the change in the direction of the velocity, but the magnitude of velocity has to be same. That is when this condition could be matched as an elastic collision. Okay, if that was the case, what would be the answer for this E? V2 minus V1. So V2 minus V1 is the final condition. So here in this case, it is towards the plus X direction. Okay, that will be the magnitude over here. Same way, U2 minus U1, still you will have the same relative velocity for the mass M2, but it will be in the plus X direction. I mean minus X direction in the situation, right? So in the numerator, you'll have the positive some value, and in the denominator, you'll have some negative some value. These two values are going to be same, therefore those two will get cancelled out, and plus divided by negative will give you the negative sign, right? So here in this case, for elastic collision, I'll get the E to be -1, okay? So whatever the case it could be, I'll just get the value to be in the negative, okay? So if it was like completely inelastic collision, in that situation, both will travel with certain constant velocity. So if that was the case, 0 will come to the numerator. So E will be equal to 0. Rest all other situation, E will be equal to negative value. I do not want negative value, okay? Purposefully, I just want the answer to be in positive. If that was the case, then I'll have to plug in extra one negative sign to remove that negative from it, right? So just I'm going to make a small tweaking this formula to get the positive value for E. I'm just going to multiply artificially by extra one negative sign to it. So we'll have like negative sign multiplied to it, okay? So this will be the formula for the E. Now let us multiply this negative sign into this term, okay? If I do the multiplication, what will I get? I'll get either V1 minus V2 divided by U2 minus U1, okay? So here in the situation, for some fancier look, what I'm going to do is I'm just going to multiply this negative sign to the denominator, okay? It doesn't matter whether you do it in the numerator or you do it in the denominator, you will end up getting the same result. Just for a fancier look, I'll just multiply it in the denominator, okay? So you'll have V2, okay, minus V1 divided by U1 minus U2, okay? So we'll have like U1 minus U2, okay? So E will be equal to V2 minus V1 divided by U1 minus U2. So that's the coefficient of restitution which you need to know. So coefficient of restitution actually means it's just the relative speed of separation divided by the approach, okay? So for elastic collision, that will be equal to 1 because the kinetic energy has to be conserved. Therefore, relative velocity of the second mass has to be same. Only thing that has to be changed is just the direction. The magnitude of that velocity has to be same, right? So that was a consideration that I've made it over here, right? Therefore, I just got the answer to be negative. If I have to get the value to be in positive, I'm just going to multiply extra one negative sign into it. So I end up getting the positive value for the particular E, which is called as coefficient of restitution, okay? Then let me find the E for the completely inelastic collision, which means the first mass gets stuck to the second mass and both are going to move with the same constant velocity, right? If that's going to be the case, in that situation, obviously V2 minus V1, there isn't going to be any relative velocity between these two masses. Both are going to travel at same velocity. For someone who is standing on the first mass, he is going to see that the second mass got collided into the first mass and both are going to travel with the same velocity. Then obviously this uh, velocity of the second mass is going to be 0 because there isn't any relative velocity between these two masses, right? Therefore V2 minus V1 will be 0. In the numerator, will get 0. Whatever value that you have in the denominator, you will still have the 0 to be this answer, right? So that's the reason why I put approach in the denominator. If it was in the numerator, if it was other way around, relative speed of approach is going to be in the numerator, then you'll end up getting the answer to be infinity, right? So purposefully I've put approach in the denominator so that I end up getting 0. Okay, so here when it was like completely inelastic collision, the answer is going to be 0 for E. Then what will be the case for the in-between situation? That's going to be in-between answer, right? Okay, so here let me change this one. Got it? That I've done in the last session. So I'll have to add one more extra thing to it. So for completely inelastic collision, you will have E to be 0. That's obvious, right? Same way for the elastic collision, you will have E to be 1. Okay, so that should be equal to 1. I have made that argument already itself. Then what will be the case for the inelastic collision? So that's a kind of in-between case, right? So there you will have E that will be less than 1 or else it has to be greater than 1. So that should be the case over there, right? So the velocity would have decreased after the collision, okay? So if the velocity had decreased, then obviously relative speed of separation is going to be less. That value will be less when compared to the relative speed of approach. So obviously that answer will be between 0 to 1, right? So just do a little bit of imagination. you'll be able to get this result, right? So if it was like 0, that's going to be the first case. That's the worst case, which means maximum kinetic energy is lost over there. And the best case will be like the complete conservation, which is like E equals 1. Then obviously in between case will be the inelastic relation. Okay, so that is 0 less than E, which is less than 1. Okay, so this is the condition that you need to know. These are the stuff that you need to know regarding the coefficient of restitution. You should be clear how I did apply in different situation. Fine. So you'll get some questions from this coefficient of restitution concept also. They'll mix this concept with the collision and they'll ask you to find certain answers, right? While doing some, I'll just tell you how to use this concept into those sums. As if now we should be clear with this theory part that you have seen, right? So now we have completed all the theory part that are necessary. Only thing that we are going to see is some extra trigonometric relations which are needed for doing sums, right? We'll see that one. I have written those trigonometric relations already over here. Just memorize these trigonometric relations, that is fine, right? I don't give you the proof of those stuff. Just Google it, you will end up getting the derivation for those stuff, right? So it is not needed anyway. So here, the first trigonometric relation which you need to remember is sine A plus B, okay? So whatever value that they given, you just have to plug it over there, right? 30 degree, 60 degree, whatever it is, sine A plus B plus sine A minus B, right? So when you do the addition of these two stuff and subtraction of those two stuff, and you're going to add it, that will be equal to 2 sine A cosine B. Okay, this relation you'll have to memorize it. Then same way you have got like cosine A plus B and then cosine A minus B, same addition into it, which will give you 2 cosine A cosine B, right? So that will give you 2 cosine A cosine B. Here these two terms are different. Here these two are like cosine. Okay, so then the only stuff that I need to get is like 2 sine A sine B, right? So to get the 2 sine A sine B, it will be like cosine A minus B negative of cosine A plus B. Okay, got it? So here A minus B comes in the front and then you have got the A plus B, right? Okay, so you will have to memorize these relation. You're left with no other choice, right? Whatever fashion that you could remember it easily, just do the memorizing stuff, right? Then if I do add these two relation, I'll end up getting the fourth one. Same way if I subtract these two relation 2 and 3, I'll end up getting the fifth relation that is needed. Fine. So let me do the addition of these two relation. So you have got like cosine A plus B plus cosine A minus B, and then you have got cosine A minus B negative of cosine A plus B. When I do add these two stuff, what will happen is cosine A plus B and cosine A plus B will get cancelled out, and then I'll just be left with 2 cosine A minus B, right? So 2 cosine A minus B, fine, got it? So you will have something like this. So that will be the final answer. So 2 cosine A, let me write it clearly. So you'll have like 2 cosine A minus B, which will be equal to the addition of the right hand side. So that will be like 2. Okay, let us factor out that one. You will have like sine, no, you will have cosine A cosine B plus sine A sine B, right? So that will be the final answer, right? So here obviously these two will get cancelled out, right? So if we do cancel out those two twos, what will we have? We'll have, this will be the final formula that you need to remember, which will be like cosine A minus B, that will be equal to cosine A cosine B plus sine A sine B, right? So the next will be like cosine A plus B. That's what we will end up getting while doing the subtraction, right? So when I do subtract these two terms, yeah, what will happen here is cosine A minus B and then the cosine A minus B will get cancelled out and these two will become positive. Therefore, you will have like cosine A plus B. When I subtract, I end up getting cosine A plus B. Okay, so you will have cosine A plus B. Obviously, those two will get cancelled out, right? So I just left the 2. I'll have to subtract it over here. So you'll have like cosine A cosine B minus, so you'll have like cosine A cosine B negative of sine A sine B. Okay, so this is the relation. So these are the relation that you need to memorize. Okay, you are left with no other choice. You'll have to memorize these two stuff, right? So once you are thorough with first 3 1, that's fine. You will be able to get the rest 4 and 5th one straight away. Just do the addition of the second and third, you'll end up getting the 4th one. Same way if you do the addition of subtraction of the second and third, you'll end up getting the 5th one, right? So you should by heart these trigonometric relations that I've told you, right? Fine. So with this, everything that are related to the chapter work, energy and power is done. Fine. So the concept we did see in this session is the elastic collision and its derivation, and then we did see what is meant by coefficient of restitution. Finally, we saw some trigonometric relation which has to be memorized, right? Everything has to be clear. With this session gets completed. Bye.